All right, now we are recording. So welcome back. And in the lab we had before spring break, we discussed rocks that form from magma. And we talked about factors like how the color of the rock indicates what the chemical composition was, like whether there's more silica in the magma or more iron and magnesium, and also how different textures relate to different cooling styles of magma, how some magma cools more slowly than others. And this week, we'll learn a little bit more about volcanic eruptions, aka when magma actually comes to the surface and is from that point on known as lava. And we'll talk about a couple of different eruption styles. And it might be worth also drawing up some notes that you have from when we did the maps lab, because some of this material is drawing from material related to topographic maps and map scales and contour lines that we learned during the first lab. And on Canvas, before you start Lab 5 itself, before you open up the actual assignment, or before you start the actual attempt, the intro page has a link to a reading on igneous rocks and volcanoes from the textbook we've been using. And there's also another PDF that focuses on the different types of volcanic eruptions, and you will especially want to reference that PDF. I'm covering some of that same information in this presentation, and I will be recording this and uploading it later. But that PDF is going to be a useful resource for answering some of the questions later in the lab. So this lab will be due on Monday, March 22nd at 11:59 p.m. And there is also a review quiz that is covering the material that we learned in the igneous rocks lab that is due on that same day. So there's a review quiz for Lab 4 also due on Monday, March 22nd. I heard a question.
Actually, I checked on Canvas and
I need to set that. I'm going to push that. I'm going to push that forward. It's set so that it's a day before that. It's set so that it's a day before that, but I'm going to push it forward.
All right.
I apologize for that confusion, but yes, that is something I will fix. Thanks for letting me know about that again. But yes, this lab will be due Monday at midnight, Monday at 11:59 p.m. and so will the review quiz based on Lab 5. And I also wanted to mention that AVC students are invited to a series of seminars that are happening over at Cal State University Northridge, and there is one happening on March 30th. And I've linked the information here, and this PowerPoint and a PDF version of it are also up on Canvas under files if people need to take a look at that. But if you are interested in becoming a geology major or are even interested in hearing what other geologists besides me and Dr. Bird or whoever else you might have encountered at AVC might do, this is a great opportunity. Also, if CSUN is a place that you consider transferring to. I also mention this because this is a potential extra credit opportunity. I've mentioned before that you can write a report after a geology hike or based on a rock sample. But at UCSB, I often let my students attend geology-related seminars and write a report based on what they learned from that. And so if you are looking to get some extra points back, you can write a one-page-ish, around 400 words or more, write up on what you learned from the seminar, and it is absolutely okay for you to talk about what you didn't understand if you do attend this and there is material that doesn't make sense to you, because chances are if you've taken one geology class, they're assuming that you have a lot more background information than you might have just after taking one geology class. But you can write about what comes up in the seminar that connects with what you've learned in lecture or lab, and you can also always shoot me an email and ask me some questions after you take your notes. But an extra credit assignment will give you 2 points that I can add to one of your lower scored assignments, and you can let me know which one you would like me to add them to. And there will be more seminars like this also. There have been some in the past. Again, I'm relatively new to AVC and I've just kind of gotten in the loop about what's being offered, but AVC students can attend these seminars. So does anybody have questions about that before I move on? Okay, cool. If you come up with questions later, shoot me an email. So let's talk about what material we're going to need for today's lab. So the first lab we did in this class was on maps, where we learned in particular about how geologists use contour maps, which show elevation to study landforms like volcanoes. Volcanoes are one type of landform. Actually, specifically volcanoes, well, volcanic mountains are one type of mountain. A volcano doesn't necessarily have to be a mountain, but different styles of eruption produce different shaped volcanic cones, and you'll see that as you go through the slab and as you look at the steepness and elevation profile of a big explosive volcanic cone like Mount St. Helens versus that of a more gently sloped volcano like Kilauea in Hawaii, which doesn't produce as many explosive eruptions, but produces more consistent low-level lava flows. Low level as in not quite as fast moving. So a topographic map, remember, depicts elevations using lines called contour lines. And the map makers choose a contour interval, which is the difference between contour lines. And that difference will be consistent throughout the map. And they choose that interval based on what makes sense given the scale of the map and the height of the features they're trying to show. So if, remember, they set the contour interval at 200 feet, then you'll have sea level, and the first line you see above sea level will be 200 feet, and then the next line above that will be 400 feet, and the next line above that will represent 600 feet, and so on and so forth. And with the contour lines all being the same elevation apart, the key thing to remember is that you want to look at how far apart they are. If they're placed farther apart, that shows that there's a longer horizontal distance as you gain, for example, 200 feet in elevation, meaning that you have a relatively gentle slope. But if they are placed extremely close together, that can indicate that you're climbing a very steep slope. You're gaining elevation without moving horizontally very much. It can also indicate a cliff. It can indicate that you're basically going up a vertical slope, like a sheer slope. And that is useful for studying volcanoes because volcanoes that experience different eruption styles have the mountains end up with different shapes, and the contour lines can indicate that. So this is a contour map of one of the volcanoes you'll be looking at today, Mount St. Helens, and there is a larger, better resolution version of this PDF that you can download within the exercise itself. So does anybody have questions about maps or anything that they struggled with last time that they want me to go over before I move on to recapping how the composition of igneous rocks is going to play into this?
Question. So when we went over the maps the first time, the map maker, the cartologist, they are the one that determine what the lines are, or like how much distance between them?
Yes.
Okay, but it's not standard for all of them. It could be anything.
Precisely. It's up to them. It's up to the person who makes the map, and that's why I said that it's up to them to pick a contour interval that makes sense given the features they're trying to show and the height of the features they're trying to show. So yes, and it's going to be specified somewhere on the map. It has to be specified somewhere, usually at the bottom or in the corner in the legend. And really, it has to be specified there. Otherwise, the map is going to be useless. Now, you will sometimes see numbers on the contour lines. They will put like 200, but they don't put numbers next to every single one. And the way to do it is to find a number that's next to one of the contour lines, and then knowing the interval, you can count. So you can, if, for example, one of the lines is 800 and the contour interval is 200 feet, then you know that the next line above the 800 line is 1,000 feet. Does that make sense? I will take that as a yes, but the contour line is particular to, the contour interval, excuse me, is particular to each map. So let's talk about igneous rocks a bit again. You had a lab on igneous rocks, and you learned that some types of igneous rocks are volcanic. They erupt at the surface, and we're talking about volcanoes this lab. We also learned that color-wise, igneous rocks can be roughly classified as being either felsic, rocks formed from magmas that are rich in silica, and particularly also in the rocks end up being rich in silica-rich feldspar minerals, or you have mafic rocks. And mafic rocks are poor in silica, but they have a lot more iron and magnesium. And felsic rocks, like the rocks making up the cone of Mount St. Helens here, are going to be usually white, pink, or light gray and rich in silica. And the important thing about the silica content in a volcanic context is that the silica gives them higher viscosity. And viscosity is a measure of how much a fluid resists flow. It can kind of be thought of as the thickness of a fluid, even if it's not literally how thick it is as a reference to the ground. But when you think of thick fluids, you think of substances like, what's something that's a fluid, but kind of if you pour it, it's going to flow very slowly. Like it's not going to just run down the slope all at once.
Molasses?
Molasses, fantastic. What else?
Or like honey?
Yep, molasses, honey, sort of sticky things. And the stickiness is key because the chemical composition of honey and molasses, in that case, it has to do with the sugar content. But the chemical composition actually causes it to flow slowly and to kind of resist itself as it flows, as opposed to, say, rainwater, which doesn't have much viscosity at all and just flows straight down the slope. And this comes into play with volcanoes. A magma that is felsic or has a lot of silica is going to be very viscous and thus really sticky because of the silica content. Silica is sticky. You don't come across silica much, but if you've ever opened a pack of beef jerky or another rice crackers or another snack that they'll have this little package of desiccant powder or this little package of desiccants inside. It says do not eat. And if you open them up, you'll find these little clear plasticky beads that are really soft, and that's a silica gel. And that you don't want to eat that or handle it too much, but that gives you a sense that silica is a sticky substance when it's just by itself. Now, felsic magmas that have a lot of silica in them, also tend to have a lot of gases trapped in them. And that's because the high viscosity of these magma makes it a lot harder for these gases to escape. And what that causes is the pressure builds up over time. And when the pressure builds up enough, that causes an explosion. So in general, felsic magmas lead to big explosions. And in volcanoes with mafic magmas, in contrast, the low silica content gives the lava a more runny texture, and the lava usually just pours out of the sides of the volcanic vent. And gas can also escape before it builds up enough to cause an explosion. So you tend to get slow-moving lava flows as opposed to large explosions. And we're not going to linger on intermediate much, but intermediate magmas can also cause explosions. Intermediate is kind of a catch-all term for magmas between mafic and felsic. And remember when I showed you the igneous rocks, I showed you some of the charts people use to classify mafic versus felsic igneous rocks, usually done in terms of silica content. So intermediate is just everything between the two extremes. And intermediate magmas can also absolutely produce explosions, depending on how much silica there is. The Andes Mountains in South America are a really good example of a chain that produces intermediate magmas and that periodically has explosions because some of those magmas have enough silica to do that. Now, one other aspect I want to mention is temperature. And we talked about Bowen's reaction series and how some minerals crystallize first in the last lab. And silica melts more easily than either iron or magnesium. And that means that it takes higher temperatures to melt mafic minerals like olivine and pyroxene that have more iron and magnesium in them. And this is an important point. You might be tempted to think that the most explosive eruptions are the hottest, but that's not actually quite true. In fact, hotter volcanoes produce lavas with more melted iron and magnesium. And that sort of drowns out and dilutes the silica and prevents it from trapping gases. So the hottest volcanoes actually tend to be runnier and in some ways safer. Lava flows are easier to escape from than a hot descending cloud of ash. So any questions about this before I move on? So remember that there's a relationship between temperature, explosivity, and chemical content. And in the last lab, we talked a bit about texture. Oh, do I see it? Sorry, do I see a chat question? Let me just double check on that. Oops, phooey. This thing is very hard to move around. This thing doesn't want to behave. I do see a chat question. And okay, fantastic. Glad to hear that makes sense. Sorry. So now when we talked about texture last class, do people remember what, in general, volcanic rocks or those erupted at the surface, what is their texture like in terms of their crystal size?
Large?
Well, think about it. What's going to have more time to cool? Something that's sitting underground or something that's exposed to the air and water right away?
Something that's exposed.
Or something underground.
Something underground is going to have more time to cool, and it turns out more time to cool is what makes larger crystals. So actually, volcanic rocks, those that erupt at the surface, tend to be very fine-grained. The crystals tend to be really hard to see with the naked eye, and the term for that is aphanitic, which means without crystals. That's not technically true because if you look with a microscope, you can see crystals, but just with your eyes, they're very hard to see. And that's because rocks sitting underground the earth is hot underneath. So magma sitting underground the surrounding material is not as cold compared to it. So it cools much more slowly, and that gives crystals time to form. Volcanoes tend to have, in some cases, almost instantaneously cooling lava. In fact, what's happening in a case like Mount St. Helens is that lava is being released in the air and cooling while it's airborne and then falling as ash and lava bombs and other projectiles. So that's the big thing with texture that you want to consider for this lab. The rocks you're going to be looking at are going to be by and large fine-grained or aphanitic because they're from magmas that erupted at the surface. Because air and water do a really effective job, especially water. Remember, I showed you the video of the pillow basalts last time. Water does a really effective job of cooling, and air does a pretty effective job as well. So you can see, so the crystals are usually not visible with the naked eye. They're often visible under a microscope. And you want to be careful with, so I'll talk about these textures, but you want to be careful with mistaking crystals with fragments of rock or with just holes. And I realize that's a little hard to do when you're looking at the sample, when you're looking at pictures and videos of samples versus being able to hold them in your hand. And I'm happy to double check things for you if needed. So aphanitic or fine-grained rocks usually form because they're cooled quickly, and most aphanitic rocks are volcanic, since when the lava is exposed to air or water, that cools it and doesn't give time for crystals to form. And we learned about a few other textures last time that will be useful for this. So a pyroclastic texture is formed when you have the fall of ash from an eruption that produces a big cloud of ash. You have the ash itself that gets lithified or turned to stone. And then you also have fragments. You have fragments of rock that are either from larger bodies of larger bits of lava that cooled, or in some cases from the volcano itself, from the cone, bits of rock get blown out by the explosion and mixed in with the ash. And that's a common, and this is often what the rocks that you see produced by big eruptions, this is often what they look like. This is a pyroclastic texture. And you'll notice that these fragments are kind of jagged because they were broken off, and they're jagged because they were broken off all of a sudden. The cone itself was broken into tiny pieces, and those tiny jagged pieces ended up being mixed in with the ash. Now, this is something you see more commonly with felsic rocks because eruptions involving felsic magmas tend to be a lot more explosive. Now, we also talked about vesicular textures last time, and I actually do happen to have a rock with a vesicular texture in my house. And you can see that it's full of holes. You can see it's also pretty dark colored. It's a little bit red, which might be hard to pick up on Zoom. But what might the red be from in this case? What chemical element?
Iron.
Precisely. Often mafic rocks end up taking on a bit of a red hue because the iron oxidizes. That's not always the case, but this is a really good example of a mafic rock with a vesicular texture, and so is this one. This one also has iron in it, it just hasn't oxidized as much. And the holes are from gas escaping, and this is a lot more common in mafic rocks because mafic lavas aren't as sticky, and the gas can escape more easily without causing an explosion. So often we can actually look at mafic rocks and look at how vesicular they are to get a sense of how much gas was trapped in the magma to begin with, because that's something us geoscientists are often interested in. And with all three of these samples here, this sort of run-of-the-mill basalt or mafic volcanic rock, this rhyolite, and this more vesicular basalt, you can't really see individual crystals that well. These aren't crystals, these are rock fragments, and these are holes. So any questions about texture before I move on? And I did see that some people had a little more trouble answering questions related to texture on the previous lab. And I do think a lot of that is from the limitations of looking at videos as opposed to hand samples. But I will most likely actually be curving that lab slightly upward just to accommodate for that. So don't worry too much about your grade for that. But any questions about texture before I move on to the lab layout? Cool. So for today's lab layout, we will be studying two volcanoes and two styles of eruption associated with those volcanoes: Mount St. Helens and the Cascade Volcanoes in Washington, as well as Kilauea Volcano in Hawaii. And for each you're going to answer some questions about a topographic map that's provided on Canvas showing each volcano. You'll answer some questions about the scale of the map, how far apart the contour lines are spaced, and so on. And you'll also study some pictures of volcanic rocks produced at each volcano to compare them. You will also answer some questions comparing eruption styles at each volcano, thinking about which one is more dangerous. And you'll also get a chance to look at some mystery rocks after doing the rest of the exercise. And that'll give you a chance to guess at what type of volcano might have produced these mystery rocks. So for those mystery rocks, you'll want to look at parameters like, are they mafic or felsic? Is it black or is it more white or gray? And then what the texture is, if it's pyroclastic, like if it's made of rock fragments, or if it's vesicular. And I'll be having a spotlight on each volcano on the next couple of slides to get you oriented. So Mount St. Helens is what is known as a composite volcano. This isn't Mount St. Helens. This is just one that shows the shape of a composite volcano really well. Composite volcanoes are often what people think of when their brain goes to classic volcanoes. Whenever I see depictions, sort of generalized depictions of the dinosaur era, like Flintstones type things, they're always full of volcanoes, and the volcanoes always look like this. This is what people think of when they think of a big explosive volcano. And remember that a volcanic mountain is actually built by the lava itself. There wasn't a mountain there first. A volcano is just a vent in the Earth's surface. And you can have a vent without there being a mountain like you have at the mid-ocean ridge. And in this case, what happens is that you have the buildup of viscous layers of lava and ash over time, making this tall composite volcano. And in the Cascade Range in the Pacific Northwest and far northern California, we have a chain of composite volcanoes forming at a subduction zone at a convergent plate boundary. And this is where the Juan de Fuca plate, which is a little microplate, is subducting under the North American plate. And that's ocean crust subducting under continental crust. And this creates mantle melting, and the mantle melting is actually what creates the magma that produces the plutons as well as the volcanic eruptions themselves. So Mount St. Helens is part of the same chain that includes Mount Rainier, Mount Shasta, Mount Mazama, which is the volcano that formed Crater Lake, and the other volcanoes of the Pacific Northwest. And they're also known as stratovolcanoes because the stratosphere is the layer of the atmosphere above the troposphere. We're in the troposphere, that's where most weather happens. The stratosphere is above that, and composite volcanoes can launch ash and other projectiles up into the stratosphere, and that can end up being scattered over the world. The big volcanic eruptions can actually produce enough ash and other airborne particles to cool the climate for years at a time even. And I don't know how well any of you remember, this would have been in 2010, there was a massive stratovolcano eruption in Iceland that more or less completely stopped air traffic between the east coast of the US and Europe for a while. And that's because this ash ends up in the stratosphere where planes can fly, and it has the potential to destroy their engines. Now, composite volcanoes usually erupt periodically with long times between major eruptions, and that's because the magma is so full of silica. And yes, actually, Jorge, that's a fantastic example. Pompeii Mount Vesuvius is a really good example of a composite volcano that has produced gigantic ash eruptions that have destroyed entire cities, destroyed the entire cities of Pompeii and Herculaneum. And Mount Vesuvius had not erupted in quite a while, but when it happened, and the same was true of Mount St. Helens. In general, stratovolcanoes erupt periodically because the gas has to build up enough for the pressure to blow and the volcano to blow its top. And prior to a major eruption, like the 1980 Mount St. Helens eruption, you might have earthquakes caused by magma moving, and you're going to have earthquakes here in general because you have a subducting plate. But you also can get earthquakes from magma moving around in chambers. You have earthquakes in Hawaii, even though there's no plate boundary there because the magma moves around underground. You'll have steam venting out. You'll also might have minor sputterings of ash coming from the cone. And this is why we have volcanologists monitoring volcanoes like this now to look for signs like that and warn people more aptly and ahead of time of an impending eruption. So, any questions about Mount St. Helens, Mount Vesuvius, or any other stratovolcanoes, which are one of the 2 types of volcanoes you're studying in this lab. Cool. Now, obviously, there's actually many different types of volcanic eruptions, and it's not quite as simple as this dichotomy, but for the purpose of simplicity, a distinctly different type of volcanic eruption that you're going to study is what's known as a Hawaiian-style eruption. And the example I have is Kilauea volcano, which is the most active volcano in the Hawaiian island chain. And remember that Hawaii is a hotspot. It's a different tectonic setting than the Cascades because you don't have subduction. You don't actually have a plate boundary at all. You have magma rising from, the best hypothesis is that there's a plume of hot material rising from the mantle. Notice the question marks on here. The geoscientists are arguing over that because it's hard to make definite conclusions about parts of the Earth that we can't visit because we cannot go in the mantle. That we will not survive that. But anyhow, hotspots, simply put, are hotter than subduction zones, actually. At subduction zones, the melting occurs because fluid gets added to the mantle, and that makes it less pure, and you don't have to have as high temperatures to melt an impure substance. At a hotspot, it's just really, really, really hot. And in general, as a result of this, hotspot lavas have a lot more iron and magnesium in them than those formed at subduction zones. And as a result of this, you get runny, less viscous, low silica lavas that allow gas to escape. And instead of exploding, they tend to erupt fairly gently out of the vent or produce these little lava fountains. Like, you don't want to be at the crater itself, but it doesn't get launched into the stratosphere. And Kilauea is erupting almost continuously, but it's not as dangerous as Mount St. Helens, relatively speaking, because it produces not very much in the way of airborne explosive particles, and the lava flows fairly slowly and gently down the slope. You don't want to touch it, obviously, but it's easier to get away from. There's just the issue of potential property destruction from the lava flows destroying your house or farm, which is definitely not good, but there's less potential for loss of human life. So that's all I have for the intro presentation. Before I stop the recording, does anybody have questions? All right then, so I'm going to open up the time for you to work on the lab then, and I will be around here to answer questions. And this presentation is also uploaded to Canvas already in case any of you want to reference it. Please, I will say I'm going to go ahead and stop the recording soon, but make sure that you read the PDF. It's the PDF. I'm blanking on the person's name. It is the it's the PDF that's not from the textbook that I've been having you read. It's from another one, and it is the person's name starts with a Z, but that's a bit of a case study on the St. Helens versus Kilauea eruptions, and that will also be a very useful reference for completing this exercise. So that is okay. Zumberge, yes. There's a PDF of Zumberge volcano pages for Volcanoes labs. You will definitely want to reference that. And yes, thank you, Viviana. You got to that slightly ahead of me. All right then, so I'm going to stop the recording and open things up for questions, or just leave the time open.